Hello everyone, I am Rika May Ispigol and I'm going to discuss with you the topic which is the soil classification. In today's objectives, at the end of the discussion, the student should be able to first, define what is soil. Second, identify the different types of soils. Third, appreciate the importance of the soil. Fourth, what is soil classification? Fifth, why we classify soils. Sixth, some concept of soils. Seventh, example of soil classification system. Seventh, basis for classifying soils. Eighth, diagnostic horizons. Ninth, soil orders of the U.S. soil taxonomy, and last, subborders, grade groups, and subgroups, family, and series. Okay, let's start with what is soil. Soil is a mixture of minerals, organic matters, gases, liquids, and countless organisms that together support life on Earth. Soil is also called as the skin of the Earth. Next, let's identify the different types of soils. The first type of soil is the sandy soil. Sandy soil is a naturally occurring granular material composed of finely divided rocks and mineral particles. The sandy soil is a soil with particle size ranging from 2.0 to 0.5 measure. This type of soil is easy to cultivate, but since it allows for more drainage than needed, it is important to water it regularly, especially during summer days. It is defined by size, being finer than the gravel and coarser than silt. In terms of agriculture, the sandy soil is ideal for crops such as watermelons, peaches, and peanuts, and their excellent drainage characteristics make them suitable for intensive dairy farming. Such examples of sandy soils are the sand dunes in the Idihan Urabi, Libya, and the areноsols or sandy soils occur throughout Europe. Another type of soil is the silty soil. The silty soil is one of the most fertile of soils. It can occur in natural soil or as suspended sediment in water column of water body on the surface of the earth. It is composed of minerals like quartz and fine organic particles. Silty soils has much smaller particles than sandy soil, so it's smooth to the touch. When moistened, it's so soapy sleek. When you roll it between your fingers, dirt is left on your skin. The texture of the silty soil is finer than sand and feels smooth and silky. Its color is usually brown to black. Its structure is similar to loam but contains smaller ratios of both sand and clay particles. It is granular material of size somewhere between sand and clay. Silty soils also serve as a smooth, water-rich, and fertile soil that is able to be used for growing most kind of plants. Okay, another type of soil is the clay soil. Clay soil is a fine-grained natural rock or soil material that combines one or more clay minerals with traces of metal oxides and organic matter. Clay soil exhibits plasticity when mixed with water in a certain proportions. When dry, clay becomes firm, and when fired, permanent physical changes occur. Clay soil is heavy and easily saturated. It becomes sticky when wet. Crops grown in clay soils. Such crops include lettuce, chard, snap beans, broccoli, Brussels sprouts, cabbage, and many more. The last last type of soil I have here is the loam soil. The loam soil is an ideal mixed and equal combination of sand, silt, and clay. It consists of 40% sand, 40% silt, and 20% clay. Loam soil is ideal for most garden plants because it holds plenty of moisture but also that sufficient air can reach the roots. For the introduction, generally we classify things so that we can make sense out of them. So we may study just a few similar groups rather than many individuals. In the past, classification of soils did not provide enough information for use and management of the soils. For instance, names such as black cotton seed soils, rice soils, olive soils, limestone soils, Piedmont soils, alluvial soils, and etc., some of which are still in common use today, are problematic. In the present-day classification, soils are classified as natural bodies on the basis of the soil profile characteristics and the suitability of the soils for different kinds of use. Okay, now let's define what is soil classification. Soil classification deals with the systematic categorization of soil based on distinguishing characteristics as well as criteria that dictate choices in a use. Another definition of soil classification, it is a dynamic subject from the structure of the system itself to the definition of classes, and finally, in the application in the field. Soil classification can be approached from the perspective of soil as a material and soil as a resource. In soil survey, as practiced in the United States, soil classification usually means criteria based on soil morphology, in addition to characteristics developed during soil formation. Let's identify the reasons why we classify soils. The first one is to organize our knowledge about soils. Second, to remember the properties of the soils. Third, to understand the relationship among soil individuals and classes. Fourth, to establish subdivision of soils grouping in a manner useful for practical and applied purposes, such predicting soil behavior, identify their best uses, and estimating their productivity. Some concept of soils. In classifying soils, soil is perceived as being composed of many individual soil units, or what we call the pedons, or natural bodies called soil. Pedon is the smallest volume that can be considered as soil. It also refers to the smallest three-dimensional body of soil layers large enough to illustrate the nature and the arrangement of soil horizons and their variability. It also varies in size from 1 to 10 meters squared. As group very similar pedons that are closely associated in the field is called polypedons. The natural body concept of soils. A soil unit in a landscape consists of a group of very similar pedons, or what we call the polypedon. A polypedon is a soil individual. Soil individuals that have in common in a suite of soil profile properties and horizons that fall within a particular range are said to belong to the same series. Examples of classification system. We have Russian soil classification system, French soil classification system, Belgium soil classification system, British system of classification, soil classification of Canada, Australian soil classification system, Brazilian soil classification system, UNESCO soil map of the world, and the U.S. soil taxonomy. Among this example, we are going to focus on the U.S. soil taxonomy. Okay, let's have the soil taxonomy. The soil taxonomy was adopted as the official soil classification system of the United States in 1965. Since that, it has gained recognition as a possible universal system for classifying systems. However, to date, no system of classification has worldwide acceptance. Let's have the basis for classification in soil taxonomy. The physical, chemical, and mineralogical and biological properties of soils as they are today that can be objectively observed and measured are the basis for classifying soils in the soil taxonomy. For instance, the moisture, the temperature, the color, the texture, structure, organic matter, percent base saturation, soil depth, and etc. are important criteria for classification. Some of these properties are observed in the field, but others require precise measurement in the lab. These precise measurements are used to define certain diagnostic soils horizons, the presence or absence of which determine the place of a soil in the classification system. Let's have the diagnostic horizons. The soil taxonomy makes use of diagnostic soil horizons for putting a soil into a taxonomic class. Diagnostic horizons also have specific characteristics that are indicative of certain classes of soils. There are two types of diagnostic horizons. The first one is diagnostic soil surface horizons, or what we call the epipedons. The second one is the diagnostic subsurface horizon. Diagnostic soil surface horizons, or the epipedons. An epipedon is a diagnostic horizon that forms at the surface. There can be only one epipedon for mineral soils: the molic epipedon, ombric, histic, ochric, melanic, anthropic, and the plagine. Soil subsurface diagnostic horizons. Diagnostic subsurface horizons form below the soil surface. Usually, they are B horizons, but diagnostic subsurface horizons may include parts of A or E horizons. Some soils do not have a diagnostic subsurface horizon. The categories of the soil taxonomy: we have the orders, the suborders, the grade groups, the subgroup, family, and the series. We have the soil orders. Every soil in the world is assigned to one of 12 orders that reflect major course of development. In the orders, there is considerable emphasis placed on the presence or absence of major diagnostic horizons. Bold letters in the soil order names below indicate formative element used as ending for lower tassa. We have the entesols. Entesols have no diagnostic subsurface horizons. It is very recent or young soil, or little if any profile development. It is formed on resistant mine soils, steep slope, and flat plains. Next, we have the inceptisols. Inceptisols is slightly more development than entesols. Young soils but beginning of profile development is evident. Well-defined profile characteristics of mature soils are yet to be developed and may have a cambric horizon. Next, we have the mollisols. Mollisols typically form under the grasslands, for instance in central U.S. Soils with a molic epipedon is thick humus-rich surface horizon, have a high percent base saturation throughout profile, slightly leach, and very fertile soils. The fourth one is the alphisols. Alphy-soils is argillic or natric soils, moderately leach. Alphy-soils have an argillic horizon. It is about 35% base saturation. It develops in humid temperature regions. The vegetation is usually deciduous, such forest in savanna. Gray to brown surface horizons. And alphy-soils is good for grain production. The fifth one is the spodosols. Spodosols have a spodic horizon. It is usually formed in humid, cool climates and occur most often in conifer forests such as England, Mitch, and Canada. It is formed in acid, coarse, quartz, or what we call the sandy bearing PM. It has low fertility. Next is the ultisols. The ultisol have a argillic or candic with less than 35% base saturation, common in US in humid tropical and subtropical regions. It is warm and humid environs. Ultisols is old, highly weathered, high degree of development, and has a low fertility. Next, we have the oxysols. Oxysols have an oxic horizon, dominated by residual accumulations of iron and aluminum oxides and kaolinite. It is most extensively weathered soils, or it's occur in tropical regions. Its color is intense red or yellow and high in oxidized iron. It has low percent base saturation or extensively leach and has a low fertility. Next, we have aridisols. Aridisols is a dry soil. It is formed in aridic moisture regimes or in dry plains. So it is dry at least 6 months. It has little leaching, high base saturation, and can be very productive if irrigated. We have andisols. Andisols is a volcanic ash soil. It usually forms by rapid weathering of volcanic ash to produce poorly crystallized aluminosilicates, or the allophane and the immogolite. Andisols are young soils. In dry climates, it can be susceptible to wind erosion, and it can have unusually low bulk densities. Last, we have the gellisols. Gellisols, also known as permafrost and frost-churning soils. Its presence of permafrost layer within 100 cm of soil surface defines this soil class. Young soils with little profile development. The cold temperatures and frozen conditions for much of the year slow the process of soil formation. It may show evidence of cryoturbation, the physical disturbance of soil material caused by freezing and thawing. This figure shows the simplified key to the 12 soil orders of the soil taxonomy. That's the end of my discussion about the topic, the soil classification. I hope you learned something, and thank you for watching and listening.